Determine if the series converges or diverges. So if I'm looking at this series and I'm thinking of the integral test, if I just jump directly into the integral test, I would have to check the three things. So this function that I'm comparing it to would have to be continuous, positive, and decreasing, and all three have to check. Well, we know this is continuous. The only place where it's not continuous is at -1. Positive and decreasing, we can analyze that too. When x is greater than 3, from 3 on, all of these y values are going to be positive, and we can do an analysis of decreasing with f prime or just look at the graph. So if I'm looking at the graph, I just put my calculator back in function mode, and if I graph this, we see that it is from 3 on, for sure it's decreasing, continuous, and positive. So the decreasing sort of checks out too. And again, I'm not formally showing it, I'm just eyeballing it, seeing it looks like it's going to be decreasing from then on. So while I may jump into doing the integral test just because we're in 11.3 and that's where the integral test happened, I gotta be careful. The first thing I should do is the divergence test. That should always be the first thing that you eyeball for a series, because that may save up a lot of time. So if I'm doing the divergence test, then I'm thinking before I apply any of the other tests I know, I'm going to pull out a sub n and see if the limit of that thing maybe doesn't go to 0. So if I take the limit as n goes to infinity of this and actually divide everybody by the highest power in the denominator and show everything, you will see that that does not go to 0. This goes to 0, that goes to 0, and we end up with n over n, which is 1. And the divergence test says that if you look at the limit of the corresponding sequence and the terms do not go to 0, either the limit doesn't exist or it's not equal to 0, then the whole series diverges. So I don't even have to bother doing the integral test, because I just showed by the divergence test that it diverges. So although all the conditions may check, I wouldn't go and do an integral on this and spend more time, because the divergence test gets me there very quickly. Again, the minute it's not equal to 0, you can conclude that that whole series is going to diverge by the divergence test. So though it may seem like you can apply it, and you may very well be able to go apply it and show it, this will be much quicker. Before we finish up that problem or go away from it, let's just quickly look at our TI. I have my TI in sequence mode, and I'm going to go ahead and put that in and look at the terms of the sequence, and I can see that the terms of that sequence are clearly approaching 1 and they're not going to 0. Also, I can look at the partial sums of this thing. So I can also go look at the partial sums of this thing beforehand, before analyzing any of this. If I put in the commands as I have sent to you guys, and I go ahead and say graph it, let me go to window, go up to the 20th term, x max up to the 20th, y min and y max, let's put like 20 also. And if I say graph, notice what you see with the partial sums. The partial sums look like a sequence that keep going up, and they don't happen to converge to a specific number. So even the partial sums on your calculator gives you a hint that this series is not going to converge. Okay, part B, does this series converge or diverge? So before I go on like the other one and do the test for the integral test with the three things being satisfied, let me just do a quick test of divergence and see if that'll save me some time. So the limit as n goes to infinity of this guy, let's see what that goes to. We can rewrite this negative exponent as e to the n squared, and that'll be infinity over infinity. Then I can apply L'Hopital, and when I apply that, it looks like I get 1 over e to the n squared times 2n, which actually goes to 0. So since the limit of the corresponding sequence went to 0, I can't make a conclusion, so it's not like I can use a divergence test and stop right there. So let's go compare this guy. It doesn't look like it's a geometric series, it doesn't look like it's a telescoping because even if I open it up, nothing will really cancel out. So the other tool I have as of right now is the integral test. So I'm going to compare it to this function and see if it's continuous, positive, and decreasing. And again, I can formally show those things, or I can go quickly look at my TI and see if those things seem like they might be satisfied. So I'm back in function mode and I have my comparable function put there. I'm going to push graph and it looks like I need to zoom in to see what's really happening. And all I'm worried about is from n equals 0 on for this series. So it looks like from right about there, right before 1, it seems like on, this function is decreasing. It's continuous and it looks positive as well. So all three of these guys, based on the graph, just looking at the graph briefly, seem like they check. Again, we could always show that it's always positive. We can see that if x is positive, the denominator is always positive, so all the y's will be positive. We can see that this is always going to be continuous because there's no trouble points in the denominator. And if we took the derivative, we can also show that from 0 on, and actually not from 0 on, from this point on, we will actually be able to find that critical point. From then on, this is always going to be decreasing. And all we care about is that it eventually satisfies these things. So it seems like the checks are ready to go. And I'm going to choose to look at the integral from 1 to infinity and not from 0 to infinity because by looking at my graph, it looks like from 1 on, it's actually decreasing. So I kind of want it to match up with what's going on when all these guys are getting satisfied. So from 1 on, it's decreasing, positive, and continuous for sure. I'm just going to go ahead and start it from 1 because even if I started at 0, I can look at my series and what happens to my series from 1 on. The 0th term, I can take it out. And it looks like if I let n be 0, the first term of the series is 0 anyway, so n essentially could start at 1. So let's go analyze this integral. It looks like it's going to be a u sub. So u is negative x squared, I guess. du is negative 2x dx. We'll divide by negative 2 and go replace the items in my integral. So I replaced my trouble point with t and the limit as t goes to infinity of this integral. Using this u sub, we've got e to the u, and then the x dx got replaced with negative 1/2 du. So we're at this point, I'll go ahead and change my limits of integration. When I have x is 1, it looks like u is negative 1 squared. And when x is t, it looks like my u is going to be negative t squared. Integrating e to the u just gives me e to the u again. I put in my limits of integration. So as of right now, I have negative 1/2 e to the negative t squared minus e to the negative 1. Let's simplify that a little bit more. So I distributed the negative 1/2, and also e to the negative t squared is the same as if you were to put e to the t squared in the denominator because of that negative exponent. E to the negative 1, I brought it back down and made it e to the 1 in the denominator, and then negative and negative, of course, positive. And now if we look at the limit as t goes to infinity, I have negative 1 over big 2e to the infinity, so this piece just goes to 0 as t goes to infinity, and it means the limit is actually 1 over 2e. This integral converges, and therefore, by the integral test, this series must converge. And again, I know I started mine at 1 because the curve was eventually decreasing after 1. This starts at 0, but if n equals 0, notice I just get 0 in this case. The term of the sequence, let's say a sub 1 I call it, is still 0, so I could be essentially looking at n from 1 to infinity of n e to the negative n squared. So by the integral test, we would say a reason, this series converges also. Now let's go do an analysis of what the graph, the calculator, will show us with the terms of the sequence and also with the terms of the partial sums. So if I'm trying to look at the sequence terms, actually I tried doing it on my TI, and no matter how much I make the y scale smaller. All it really shows, as you can see here, is the first one when n is 1. The rest are so small, these become, actually these should be when n is 2, they should be 2e to the negative 4 and 3e to the negative 9 because I keep squaring my n values. So these terms of the sequence are so tiny that the TI had a hard time. I played around with the scale, it wasn't showing it, but the point is that the actual terms of the sequence that you look at keep getting lower and lower and lower, the terms of the sequence, and we showed that here because the terms of the sequence go to 0. Therefore, there's a chance that this thing may converge. Now, looking at the partial sums as a sequence, now let's see what happens with the partial sums of this sequence. So S sub 1, S sub 2, S sub 3, S sub 4. This series generates these partial sums, and let's go look at the graph and see what happens to those partial sums. So I'm going to go to Window. Again, I've changed my Y scale. I'm just going to go up to the 20th term, make sure my X is 20, and I'm going Y up to 1, and I'm making the scale smaller so in hopes that it'll generate something. I push graph, and it does actually. It shows me that the partial sums seem to be leveling off, and this thing probably converges because it doesn't seem like the partial sums are going off or oscillating in any way. So just by looking at your TI, the terms of the sequence better go to 0 if there's any hope for it to converge. And by analyzing some partial sums, you should eventually see the partial sum sequence leveling off somehow. And with the integral test, we showed that this thing should converge. Okay, does this series converge or diverge? Again, I'm going to quickly pull out this guy and do a quick divergence test to see if this will be quick. But when I do that, the denominator gets big, ln of n squared gets big, so this thing goes to 0. That means I have no conclusion here, so I have to analyze this guy some other way. If I spit out a few terms, this won't look geometric, and it won't look like it's going to be telescoping either, so I resort to the other tool we have, which is possibly the integral test. So if I compare the series to this function, I have to make sure it's continuous, positive, and decreasing. So we're going to quickly go look at our TI. So I'm back in function node. I have that input into my TI. I'm going to push graph. And I see this graph. I know there's something going on at 1 because we know ln of 1 is 0, and there's something going on at 0. But if I zoom in a little bit, maybe let's go to the right and zoom in from 2 on. It looks like from 2 on, I do have a decreasing positive continuous curve from this point on where my series starts. And again, you can check that there are only trouble points are 0 and 1, and that doesn't happen here. Series starts at 2. It's always positive because when x is positive, this is also positive, and it is decreasing. And again, you can look at the derivative to show that it is for sure decreasing. So it meets this criteria. That means I can go on and look at the integral. So we look at the integral from 2 to infinity of this function. This is an improper integral. Look at the limit as t goes to infinity and analyze this, which it looks like it's going to be a u sub. So if I let u be ln of x, then du pops out this 1 over x dx business. So this piece gave me 1 over u squared, and then the 1 over x dx gave me du. I changed my limits of integration. X is 2, that's ln of 2, and then x is t, that's ln of t. So this integrates to u to the negative 1 over negative 1, so I basically have negative 1 over u with these limits of integration. So now I have the limit as t goes to infinity, plug in the ln of t, minus a minus 1 over ln of 2, and we can tell that as t goes to infinity, ln of t will go to infinity, so I have 1 over big, which goes to 0. So this whole improper integral goes 1 over ln of 2 and therefore converges. So we can conclude that by the integral test, since the integral converged, our original series also converges. And again, if I look at my TI, the terms of the sequence will go to 0, and the terms of the partial sum of the series will level off and go off to some certain number. We haven't found that number. All we know is that it converges.